Welcome everybody. In this video we are going to speak about the position transformation and orientation transformation of a planar model of a car, and this whole thing will be done in Python. So the idea is that we have this simplified model of the car looking from the top in XY coordinate system. It is defined by 5 points. Of course this geometry can be made more realistic, but now to understand the core idea of this transformation, it is more than enough. And the goal is that these 5 points are transformed in such a way that when the car is moving along this red path, the blue model is nicely following the direction of the road, and it is always, the center of the model is always on the track exactly. And we will see that the core idea is to use a transformation for the position of the center of the model, and additionally we also need an orientation transformation, so we need to rotate the model, and this whole thing will be implemented in Python to really understand what's going on in detail. Let's jump into the Python code. First we need some libraries from Python like NumPy, matplotlib, copy and time. At the beginning we are specifying the track itself, the red one, what we have seen in the background. Yeah, so this red track will be created first in this first section of the code, which is user input, let's say. Okay, so we are defining a maximum time during the car is moving. This time is divided into 60 pieces in this code. This number can be changed to anything basically. The 30 seconds will be divided into that amount of equally distributed time instance with this linspace command. And here with these two code lines we are specifying the x and y coordinates. So the red path is basically created by a series of points of xy pairs, of course, or points defined by xy coordinates, and also the time is specified. So as the time is progressing, then the car will move along this path nicely, and it is just for the sake of simplicity, it is created as a combination of sine and cosine function, just to make it simple. Otherwise this 8-shaped path exists in the car racing competitions. So we are defining these two coordinates, and there are some parameters. So omega x and omega y, which is just denoted by wx and wy, are responsible for some frequency, so how fast the car is going along. If we would change them to the same number, you can also create a circle, so you can modify the path, and also the sizes, 10 meter and 20 meters size of the track can be also changed. Yeah, so this v and h are the width and the height of the track. Next step, which is still some kind of input data, is to define the 5 points of the car, and these are actually specified in an array. We could also use matrices, but it is better to use arrays because they are more flexible than matrices. So we are just defining the 5 points as pairs of xy coordinates, but it's a little bit tricky because there are 6 pairs here of coordinates, because the first one is exactly the same as the last one, because there will be some lines connecting these points, and the goal is that the last point, this is the 5th point, which is I think this one should be also connected to the first point, which is this one here. So there are 1, 2, 3, 4, 5 lines, and the 5th line is actually connecting the last point to the first one. Yeah? So we can define these points, and it can be also modified. Yeah, also the size of this array could be modified, it doesn't matter. or the code is handling it automatically. And then we are going to visualize everything. But before that, we need to do some further calculations. As we know, as the car is moving on the track, it is always parallel to the track because its velocity vector is also parallel to the track. So let's explain it quickly. So let's say the car is at this point, at this moment, it has x and y coordinates. This is the center point of the car, and what we know is that the velocity vector is always parallel to this track. So the red one is the track, and the velocity is tangential or parallel to the track at this point. So this is the velocity vector. It has also two components, vx and vy, and these components are calculated in the Python code by just calculating the derivative. So we could say that vx is basically equal to the derivative of the position coordinate x, and vy is equal to the derivative of the position coordinate y. So we need to differentiate them by time, and this is what we will do in the Python code as well. Of course, we are doing it for now in a closed form. So there's a sinusoidal and cosinus function for cosine function for the position. So it is just the derivative of them with respect to time, which is done analytically. And we also can calculate that the angle of the car looking from the top can be calculated from the components of the velocity vector with arctangent function. So let's go back to the drawing, and we see that this angle here, which is theta, can be calculated by the two components of this component and the other component of the velocity vector. And this theta is actually stored in an array because basically the lim space also serves as an array as a result. So therefore xc and yc will be an array because t is already an array, and here we are also using t when we are calculating the velocity components, and t is still an array, so these components are also stored in an array for all time instances. And finally arctangent function is applied for them, which is also giving us the theta angle as a long array of theta variables. When it's changing in time, each element in the array will be corresponding to a certain time instant. And now we can go to the visualization. The first plot will show us the time histories of the xy position of the car and also the orientation of the car represented by theta, and also we will plot the velocity components vx and vy. So the dashed lines will be the velocities and the black one will be the theta angle. Let's run the code now. So on the upper left panel, this is what we see. Okay, so the continuous lines are the xy position, the dashed lines are the xy velocity, and the theta angle is basically the black line in radians, of course. And the next what we will see is the theta angle, a zoom on the theta angle. So the graph here is basically identical with this one, but a little bit more optimized from the point of view of the axis scale. So this is nothing new basically, but the car shape is also plotted here. We are just taking those variables which we defined at the beginning. Yeah? So this was an input data for the geometry of the car, and these points are just visualized in this plot. What we can see on the right hand side of the panel. So this plot is visualizing the 5 points of the car, and finally we have a last plot down here, which is basically the moving animation. The important thing is that we need to specify this line, otherwise it will not move. So it's enabling this interactive mode when the objects are changing position on the plot. And furthermore, what we need is that we are creating an object which is the same what we see up here. Yeah, so this is just a plot for the car points. Yeah, this is the same thing, but we have a name for it, and we define that this is existing on this subplot on the right bottom corner. And basically this object is created, and the XY coordinates in this object will be always updating as the car is moving. Yeah, and basically there is a for cycle, which is the soul of the whole code, and you see that this animation car object is always updated. So as we said, the X data and Y data are always reset with this set command. Yeah. And this whole thing is in a for cycle, and the for cycle is going along the time. And itmax is basically the variable which tells us how many pieces we use for the representation of the 30 seconds time duration. So we go through the time, and at every time instant we need to calculate the position of the center of the car, which is just simple because already we created this XC YC array at the very beginning in the input data phase. Yeah? And we are just taking the corresponding index element from these vectors, so they are just representing the position of the center of the car. Very easy. And this point is in the local coordinate system. It is basically this upper one is the 0, 0 point. So relative to the 0, 0 point there are 5 points, and the 0, 0 point is the point which will be always moved on the red line. Yeah, so P is basically the center of the car, but we also need the rotation information, and this is why we calculated the theta angle, as you remember. So theta angle was calculated by this arctangent function, and we are just putting together a rotation matrix in a planar situation, which is quite simple. 2 by 2 matrix in a plane with some cosine and sine terms. And once this rotation matrix is ready, we can start to transform each point of the car one by one. So therefore, each point of the car one by one. Therefore, we have another for cycle within the time for cycle, and this second for cycle is going along the points. So first point, second point, third point, fourth point, fifth point, and that's it. And 6 points, of course. Yeah. So it's going through the 6 points, and for each point, we say that the local position of the point is just taken from the car shape of, array defined at the beginning, yeah, here. So we take the X and Y component, so 0 and first indexes for X and Y, and the other index is going along the 5 points. Okay, so we just create a vector of 2 numbers in an array, and this is the local position of the point. And when we want to create the global position of the same point, so for example, I have this point here, this right front corner of the car. The same point will be here in the global system, yeah, this one, and we are just applying the formula what we have for orientation and position transformation. So the global position of the same point equals to the rotation times the vector in the local system plus the position transformation vector, let's say p. Okay, so this is the very formula which is used in spatial transformation of orientation and position together. And then after it's ready, we are just putting back to this car shape array. We are just putting back the two components of the vector. And there is just one more issue. So in L is always meaning that this is in the local system. So this is the car shape vector in the local system, and now we calculated the car shape in the global system. And this copy dot deep copy means that if we try to create a copy of a variable, we are not just going to introduce a different name for the same variable, but we are really copying it in the memory of the computer, and that's why we need this copy deep copy, because this variable will remain always the same what we defined at the beginning. Yeah? The shape of the car does not change, but this is a variable in the global system. The position of these points will be always overwritten by the code, so it is continuously changing. So these are technically two different variables, and if you just say this, the program keeps these two variables as one, but you can refer to them in two different names. So this is a quite serious issue in Python. But okay, let's go through it. So yeah, we have the points, and basically we arrive to the end. So with these transform point, we are basically updating this anim car object, which is just a line plot, this blue one. So we are updating it, and it will move accordingly to our calculations, and these commands are just for making the animation move. So let's again see the running of the code. Yeah, that is it, and we will see how it looks like again. Okay, so the idea is that each point of this blue object are always retransformed to a new location in the space, and we call it transformation to the global coordinate system from the local coordinate system. Thank you very much for your attention, and hope you find it useful.